Hello everyone. Today I'm happy to give you a presentation about our paper. The title is the Devil's Whisper, a general approach for physical adversarial attacks against the commercial black box speech recognition devices. My name is Chen, and this is a collaborative research with the Chinese Academy of Science, Florida Institute of Technology, Boston University, and Indiana University Bloomington. Okay, so now let's start to go to the presentation. As we all know, today, speech recognition technology is widely used in our daily life. For example, cell phones, smartphone devices, and computers. So it's very easy to use these devices to do lots of things just by voice. For example, we can talk to our Google Home to order a pizza, to open the door, or to do lots of things. However, when we enjoy the convenience of the speech recognition technology, there has been many attacks towards speech systems. For example, traditional attacks. Traditional attacks usually include hardware-based attacks, for example, like stopping attack. Today, there is a new type of attack called adversarial attack, which is based on adversarial examples. So what is adversarial example? Basically, adversarial example is a benign sample added with very small perturbations. So this new sample can change the results of the machine learning model totally. Like if I have a benign audio sample, good morning, after an attacker adds the very small noise onto it, then the new sample would be recognized as the open the door by the machine learning model. However, for human beings, we will still understand it as good morning. So this is the audio adversarial example. Later in the presentation, I will use AE to refer adversarial examples. Okay. So in this paper, what we want to do is to propose a method to generate audio AEs for commercial black box speech devices, for example, Amazon Echo or Google Home. And this approach needs to be general, practical, stealthy, and automatic. So this is why and what we want to do in this research. Okay, next, let's go into the approach. First, let's take a look at the overview of approach. Recall that in this paper, our aim is the black box platforms, including the commercial speech APIs and the commercial speech devices like Amazon Echo. And to achieve our goals, first, we propose that we can use the transferability-based approach, shortly as TBA approach. So in TBA approach, we just use the gradient descent idea towards the white box model and generate a bunch of AEs, and then use these AEs to attack black box devices use a transferability-based idea. Obviously, the success rate may be not very high because, as we all know, the white box model may be very different with the black box model. So based on this, we mainly propose another idea called alternate model-based generation approach, shortly as AGA. So in AGA method, we normally propose that we can use one large base model, a local large base model, with one substitute model to do the ensemble AE generation. So for details, now let's go to the details about this search. First, I would like to introduce the what is a substitute model we use in this idea. So basically, substitute model is a local trained model to simulate the black box model. So we need to have a bunch of audio files and labeled by the target black box model, and then we use the audio files and the text label to train a local model to simulate the black box model. So we are going to use this substitute model in our idea. Okay. So next is details. Okay. Recall that we are going to use the substitute model, right? So to train this model, first we need to have the training set. Here, training set. The training set is labeled by black box model, and here we propose that we can just use the limited number of phrases because our aim is to attacking the black box devices. So we are only interested in the several phrases like open the door, like transfer me the money, like call 911. So we can only use just several number of commands. And then we propose that we need to use the data argument to extend our training set, because if we only use a limited number of phrases, then the training set must be very small. So we need to extend it. In detail, we are going to add noise and change voice speed on this data set. Oh, by the way, adding noise has another advantage, is that, as we all know, the black box model must be trained on the lot of data set and must include the noise-based voice, like because the black box model must consider the real-world cases, and in real world, our voice must contain many noise. So adding noise can help us to simulate the black box model in a better way. Okay, so this is the training set. However, here we have another question. Because our local substitute model is only based on the number of phrases, so we may have the overfitting problem, because the limited number of phrases, they only contains several words, several phonemes. So overfitting problems may exist in this model. To overcome this problem, we propose that we can use another supplemental set. Another supplemental set may be open source voice data for training, and you can just use any online set like Cody data set, like mini library speech, like Wave2Net. So by adding this large supplemental set, we can combine our training set with supplemental set to together train our substitute model. So by doing this, hopefully we can solve the overfitting problems. But here we have another question. Because our substitute model is going to simulate the black box model, like Google model, like Amazon Echo. But as we all know, the Google model or Amazon Echo is based on the very large data set. So our local substitute model is very difficult to simulate the black box model, because this model would be very small model. I mean, compared with the target black box model like Google model. So here we propose that we can use another large base model to help our local substitute model to do the ensemble generation. This large base model is already trained ASR model, like called the Adversarial model. Then by doing this way, we can use a large base model with a substitute model to do adversarial sample ensemble generation to overcome the small model issue. Okay, so this is a high-level idea. When we generate our AEs, we use the momentum-based iterative fast gradient method called imec-COSIC method. Specifically, we use song or music as our original song, as our carrier. And we use the PDF-ID sequence matching method, which was used in commander song method. But different with commander song, here we use the momentum-based idea to improve the transferability, and this was not used in commander song paper, I think. Okay, so this is the details in the generation process. Next, let's see how we can understand our attack and why it can be successful. So first, recall that we have a large base model, right? This large base model is trained on the very large data set. So basically, it can generate our speech features in a coarse-grained manner. And then our local trained substitute model can fine-tune the features to attack black box model, because this substitute model is for simulating the black box model, right? Okay, here I have his example, and this example is a real example in our experiments. The target command is clear notification, and as we can see, in base model AE generation, first it can be recognized as the lyrics of the music, and then after several of iterations, it can be recognized as I don't. Then in the substitute model AE generation process, it will be recognized the notification, and after a bunch of iterations, it would be recognized as clear notification. So we can say step by step from the base model AE generation to substitute model generation, from a coarse-grained manner to fine-grained manner. Okay, so this is the understanding of our attack. Then let's see the results evaluations. First is the device attack effectiveness. we can see that for our proposed AGA method, for the Google Assistant, Google Home, Microsoft Cortana, Amazon Echo, and IBM Wave2Air, we can achieve very high success rate. And notice that our effective distance is from the 5 centimeters to 2 meters, which means that our attack is very effective in real-world distance. And we also did a robustness test, which means that we played our adversarial sample for 30 times, and we want to see how many times can be successful. All tests are under the same test environment, the same distance, the same position, the same devices, and we can see that over 76% of our commands, they can achieve 10 successful cases over 30 total playing tests, which means that our attack is very successful and they show strong robustness in real world. Okay. We also did the human perception evaluations on Amazon mTurk survey. We can see that 84% of users, they think the sample sounds like a normal speech or just noise. And only 1.4% of users, they could tell 50% of words in the target command, which means that our human perception test is very good and our adversarial sample is still enough. Okay. We also did evaluations on other simple approaches. For example, what if we just mix the music and the command together, use Adobe softwares, and compared with Devil's Whisper approach? You can see that under similar success rate with Devil's Whisper, this approach will have the very bad human perception results. Only 6% of users, they think the sample sounds like a normal speech or just noise. This means that our Devil's Whisper is very effective compared with other simple approaches. Okay. Next is a conclusion. This is a final part. In this paper, we propose the first adversarial attack against the commercial speech devices such as Amazon Echo, Google Home, and we can overcome the black box challenges. And this is towards speech system, and this is more complicated rather than image system. Our attack is effective and stealthy, and this is a normal idea to do the model ensemble generation. Okay, so it's a conclusion. And thanks for your joining and hearing. And if you have any questions, please feel free to ask in the next section. Okay, thank you.